Alright, so what's the key to doing maximum minimum area questions for quadratics? The first thing is you need to get the equation, but once you get that, what form do we want to find? So whenever you see the word maximum or there's something minimum, when you see max or min, that means we're going to need to get the vertex form. The vertex form of a quadratic looks like this. Right? And to do this, we need to know how to complete the square. Alright, so let's go ahead and get our first equation. So it says a rectangular playground with one side being attached to the school. So here's our school. And then we need a chain link fence in the form of a rectangle. And that is 400 meters long. It's asking us what the dimensions are. So let's give this W and this L. And then we can see that we can find a relationship. It asks what are the dimensions of the field with the maximum area, and what would that maximum area be? So because it says maximum, that means I'm looking for the vertex form and I will need to complete the square. So let's find out what our relationships are. Well, if we let W represent the width in meters, and we let L represent the length in meters, then we can look and figure out our relationship. Well, there's two widths and there's one length, and that totals 400 meters. So that means 2 times W plus L equals 400. So that's to do with the length of our chain link fence. But we also need a relationship for the area because it asks us to maximize the area. The area is equal to length times width. So what we're going to do, how do we get our quadratic? We take this relationship right here and we're going to solve for L. So if I take L, and I will need to subtract 2W from both sides, and get this. And here is our relationship for L in terms of W. So I put that in here. Instead of L, I put 400 minus 2W times W. Now some students might ask, well, why don't we solve for W? You can, but you'll have to divide all your terms by 2, and then you'll have a fraction, and this just makes it a lot easier. So let's go ahead and multiply this out. 400W minus 2W squared. This looks like a quadratic now. And what we want to do is maximize it. So we want to maximize the area. And let's make this look like a quadratic how we usually do it. Let's put our A term first. If you're not sure about the sign, if there's no sign in front of it, then it's positive. And on this one, there's no third term. That third term, C, is 0. So now we have this in standard form. That means some coefficient times W squared plus the coefficient 400 times W plus 0. That's our C. That's our A, our B, and our C. So we want to maximize this. So we want to get into vertex form. And we're going to do this by completing the square. So we don't need to isolate our first 2 terms for anything because the third term is 0. So we need to make this a perfect square. But we are going to factor out a -2 first. So when I factor out the -2, I'm left with W squared. I'm dividing by a negative, and I'm left with 200W. We're not factoring out the W's because we're making these two terms into a perfect square. We just want to factor out the coefficient. So what we'll do next is make what's in here a perfect square. So that means we need to add a third term, and we're going to take this and divide by 2. So this term, we're going to leave it. We're going to take this negative 200. We're going to divide by 2, which is going to give us 100, negative 100, and we're going to square it. So I've added this extra term, so I need to subtract that extra term so that I really didn't change it. If I took these two numbers right here, I would get 0. But I don't want to do that. What I want to do is I want to take these 3 terms and make them into a perfect square, because that's why I chose this one as negative 100. So whatever number's here, put your negative 2, write down your bracket, and what I'm left with is W, whatever's inside the bracket goes here, it's negative 100, and that all will become squared. So if I went and squared all this, the first term squared, the second term is the first times the second times 2, which would be negative 200W, and it's the last term squared. I like to put that negative inside the brackets. That would square to 10,000. But the reason I leave it in the brackets so that I know what to put right here in these brackets down here. So now this term I'm going to multiply 100 times 100, and there's a negative there, so 100 times 100 is going to be 4 zeros, and then close the square bracket. So to finish this off, I want to distribute this negative 2 inside the square brackets. So that first one just ends up being like this. And now I have to multiply negative 2 times negative 10,000. So negative times a negative, that will be positive, and this is going to be 20,000. So now when I look at this, I need to make sense of it in terms of our question. Alright, so what this means is that if we think about our x and our y, this would usually be an x here. This is talking about our width. So essentially our vertex would look like 100, comma, 20,000. This right here is our width dimension, and this right here is our area, because that would be our y part of our vertex. So what this is saying is with a width equal to 100 meters, we would maximize the area at 20,000 meters squared. So we're not quite done the question, I think, because it asks us what the dimensions are. And so I would need to figure out what the length is. So if I go back and look at what my equation is for length, it's 400 minus 2 times W. So let's go ahead and do that. And that gives us, I'm subtracting out 200. So that gives us 200. So therefore, the playground will have a maximum area of 20,000 meters squared with dimensions of 100 meters by 200 meters. Okay, and there's my therefore statement. I'm making sure that I have units, and I've made a complete statement.